Hello and welcome to Open Logic. In this video, we'll look into memory arrays. Previously, we have looked at a memory cell and its operation. Let's say we have several of them. For simplicity's sake, let's say we have 64 of them. We can label them from 0 to 63. Each of them can be accessed independently. Now, traditionally, we need a 6-bit address, which can hold a value ranging from 0 to 63, and we need an address decoder to select which memory cell to access. Say we provide 0 at the address bus, the address decoder will select memory cell 0. If we provide 2 or 10 at the address bus, memory cell 2 can be accessed. And if we provide 63 or 111, then memory cell 63 can be accessed, traditionally. In reality, memory cells are not structured totally independently. There are many reasons. For example, you would need 64 sense amplifiers if all memory cells are really independent. Instead, the memory cells are structured in an array manner like this. First, let's label them. All memory cells in the same row are controlled by the same enable line, and all memory cells in the same column are sharing the same data line. In this structure, one data line is attached to 1 sense amplifiers, and therefore we only need 8 of them, not 64. Now, if we combine all connections, you can see that the 6-bit address can be divided into two 3-bits. 3 of them are used to decode which of these 8 rows, and another 3 to decode which of these 8 columns. Say we provide 0 to the address bits, and these 3 bits will select row 0 and enable these 8 memory cells. And these 3 bits will select column 0. At the end, memory cell 0 is being accessed. If you remember the operation of a memory cell, we need to enable the transistor first, then only we access the data of the capacitor. Following this sequence, we can divide the address decoder like this. One row address decoder and one column address decoder. And since we can provide row and column address at different time, we can create another component. Let's call it address arbiter, where it has 3 input address pins instead of 6. Now you need to send the address separately, row address first, where it is driven to row address decoder, and column address second, where it is driven to column address decoder. The advantage of this structure is that as a hardware, it has fewer pins, which is a big deal, because more pins means higher cost. However, cheaper cost comes with a more complicated operation, where you need to send the address in 2 parts. Alright, let's redraw the diagram. It is the same. Every square is one memory cell. This is cell 0 and this is cell 63. Question: if I have 1 byte of data, how is it stored in the array? Is it stored like this? And this is somewhat a trick question. No, the byte is not stored like this. Because every cell has its own address, you will have to select address 0, write 1 bit, and select address 1, write the next bit, and so on and so forth, which is time consuming. The truth is, several arrays are stacked together to form a structure called bank. Not a very intuitive name, to be honest. Now, if you want to write 1 byte of data, the 8 bits are distributed to every array. Writing to address 0 will write cell 0 of all arrays. This is writing to address 1. This is writing to address 2, 3, 4, 5, 6, 7, 8, and so on and so forth. This 8 arrays configuration is also known as by 8. In currently existing DRAM, there are also by 4 and by 16 configurations. We will discuss more about this in future video. Before we move on, there is another terminology, and it is represented by this imaginary plane. This plane is called a page. Why? Because if you look at it, this is one line of data, this is another line, and so on and so forth. If we treat this as a book, not a bank, this is similar to a page in a book, and these are sentences in a page. And this is the second page, and this is the third page, and so on and so forth. The size of a page is number of columns times number of memory arrays. Now let's look at operation at the memory array level, or to be exact at the bank level. Note that for all operation on this memory array, the same operation is happening to all arrays in the bank. Now we know there is a sense amplifier at every column, and we know there's a row address decoder, and there's a column address decoder, and there is an address arbiter. To complete the picture, there is also a data buffer. Now let's look at the writing operation. First, we send a row address, and it enables the whole row, which basically means the whole row is being loaded to the sense amplifiers. Next, we send column address, which decides which column to be written to. Then we send the data. The column address decoder will decide which column the data would go, and at the end, the values at the sense amplifiers are loaded to the enabled row. Now, these cells which are enabled but not being accessed, I couldn't find much information on them, so I'm making an educated guess that they are being refreshed. Now let's look at reading operations. Well, it's pretty much the same. We provide a row address to enable one row. The whole row is loaded to the sense amplifiers. Then we provide a column address. It selects which column to be loaded to the data buffer, and the data is sent out. Also, the values at the sense amplifiers are refreshed back to its row. Alright, and that's all for this time. In the next video, we'll look into dual inline modules DIMM. If you like this video and want to see more of them, don't forget to like, share, and subscribe.